mortal remains of some idiot named Dan Anderson. I'm run a small company called Anderson Effects. We consult to the ESD trade, but prior to that, for some 20 odd years, each a little odder than the last, I was vice president of a company called Richmond Technology on the eastern edge of San Bernardino in a little town called Redlands, where the city limit signs are on the same post, and the head of the mafia is Polish. We got one yellow page. Relatively small town. What we do there at Richmond was to extrude and laminate and put together all the various military packaging films required by medical packaging and the exigencies of the space age. We were one of the first people to make clean room packaging. And we also were the people who came up with antistatic plastics. We were the inventors of pink poly and all the antistatics that led to the present rush of interest in ESD control. Came about in a funny way. How many of you guys remember when the clean rooms came in, about 1958 or early 1959? Suddenly a brand new set of rules. Incidentally, if you don't pay attention, the whole thing's for nothing. I smoke these because I don't want to die of nothing. But when the clean rooms came in about 1958, NASA had traced about 75% of their missile launch failures when the thing either blew up on the pad or for whatever reason failed to complete the mission. They traced that to what they like to call particulate contamination, which is a $4 word for dust, right? You get a grain of dust in a relay, it's not going to close. You get a grain of dust in a liquid oxygen valve that snaps happily and energetically shut on it, that promptly ignites. What that does is to clean the pad for a 400-foot radius. You get some rather interesting reactions from microscopic junk you could not readily detect with the naked eye, so NASA quite naturally put in the clean room. NASA, after all, was faced with a reliability requirement that is hard to imagine, much less to match. How do you rehearse a takeoff from the moon? Man, that has to work the first time, Charlie Brown. You got one shot at that one. There is when you press the button on the limb, you know it's for the takeoff, and one of the 400,000 electronic devices in there quits, we will see you around and around and around. You're not coming home, man. And so NASA quite naturally wanted to do everything possible to assure as nearly as possible the flawless functioning of each device on its first try. So they would traditionally make 500 circuit boards and fly 5 of them, do SEM scans on every part of every piece. They were not kidding, it was for serious. Now, once you had cleaned a part in one of these clean rooms to the gnat's whisker of cleanliness with ultrasonically agitated triple distilled freon or something like that, you emerged from that bath with a part that was about as clean as humans knew how to get it. And they had to assure or maintain that degree of cleanliness during its handling and storage. So they went out and bought some nice clean polyethylene bags from the local supermarket, totally unaware of the fact that all commercial polyethylene was dusted all over its surface with talcum or cornstarch to keep it from sticking to itself. Incidentally, ma'am, that's cornstarch. It's talcum if it's for industrial use, and it's cornstarch if you're going to eat a food product out of the bag. It does not do to eat talcum except under rather specialized conditions. At any rate, what they did, right away the microscope said tilt, and 3 guys about 1960 went into the production of what they like to call the world's emptiest bags. They extruded polyethylene in the form of a closed tube, around a bubble of filtered dry nitrogen, and inside of that tube was not only clean, it was sterile, since no self-respecting germ could live at those temperatures. And they rolled it up like a flattened fire hose in the form of what they like to call lay-flat tubing. You've seen it over your laundry, that continuous tube. The inside of such a tube, properly made, is the cleanest achievable plastic surface. It is cleaner than you could clean something to be, because anytime you rinse something with any sort of a bath, you leave an inevitable percentage of residue, whereas this was born clean. It came out, had never even seen an atmosphere, right? And they would rind that up in that flattened fire hose form. You've seen that stuff. Presuming this, however, to be see, that was made from a continuous tube. Presuming this to be a plain polyethylene bag, not an antistatic one, you can see it was made from a tube, and to make that thing into a bag, you simply sealed it here, sliced it here, and sliced it there. And you had a bag of whatever diameter lathe for that tubing you had and the length that you cut it. And the inside of that tube had never even been exposed to air. Neither of those operations had ever separated the walls. So you shipped it down to Cape Kennedy, and the guy in the ultra clean room wearing his ultra clean, non-shedding bunny suit in a room where they would have fired you for writing your name with a pencil, because the dust off the pencil point is not only dirt, that's conductive dirt, and it dead shorts microelectronics. Couldn't go in a room like that with dandruff. I was free to go in. The average guy was not. But they greased your eyebrows and put a snood on your beard because they flat weren't kidding. A grain of dust could and occasionally did kill a man. Now, the guy's got to put the object into the bag, right? So he inevitably has to do that. And in so doing, he sucked into the bag the first atmosphere he'd ever experienced, including everything shedding off the guy, right? Secondly, by separating those walls of normal plastic, he put a hellacious static charge on each one of them. And they became, in effect, dust magnets, and every airborne particle for 40 feet against the wind used to head unerringly for the critically clean inner walls of that bag. We used to have letters from Rockwell. Dear sir, the ultra-clean polyethylene bags that you have furnished to this facility contain red hair, and my red-headed technician said so. Man, there was nothing in those bags when they left, but that was happening. Nobody was seeing it happen. The other thing was that wasn't the worst problem. Polyethylene is, after all, rather soft plastic, rather like a wax or a candle wax, which it chemically resembles. And if you put a sharp-edged object in that bag, it would get busy by flexure and abrasion, combing off polyethylene dust inside the bag, and the bag was sort of self-contaminating as far as particulate of any kind. Wasn't too much problem. It wasn't shorting, but in the liquid oxygen situation, that's powdered oil, and that's not devoutly to be wished. That's high explosive. So right away, about 1961, when I was young and sanitary, I was working for Allied Chemical, and we switched the nation over to the use of nylon bags. The ladies are familiar with it. You cook a turkey in a nylon bag, and it melts at 428 F, give or take nothing, right there. But it's tough and abrasion resistant, so you could make nylon bags in exactly the same way, put the clean object in that bag, it didn't scrape off particles, overwrap that with the cheaper polyethylene bag, which provided to some degree the missing moisture vapor barrier, because nylon allows moisture vapor to pass through it as if it is not there. Practically nothing else does, not oils, not odors, not freon, but moisture vapor goes right through nylon. It makes possible dustless desiccants. Polyethylene is not a very good moisture barrier, but it's a lot better than nylon. At any rate, what they began to do, nylon became the inside bag. It was known as the intimate barrier, meaning nylon was always right close to whatever you were proudest of, and nylon is often observed in that configuration. Anyway, it dawned on NASA that these two materials had one thing in common. That was that they simply generated static electricity like unto it was going out of style. Now, I got to take all of you guys back, and the ladies as well, to General Science 1 for a minute. This is not designed to talk down to you. When I lecture at JPL or MIT or places like that, I often wonder what I'm doing there with my $4, because the audience has generally, universally forgotten more about electronics than I am ever likely to learn. But we find it universally true that among the best educated scientists is somewhat of a distorted or misconceived notion of how static electricity works, because the last time most of you did much with it was General Science 1, when you rubbed a cat and played with the pith balls, right? It's about like that. Okay, all of a sudden that's got up on its hind legs to haunt you. So we start from scratch. When I was 40 years old, I was considered myself educated. I'd been to 2 county fairs, 1 goat roping, and a buzzard auction. I figured that covered it. World don't have too many terrors after all them things. But at age 40, I was a graduate engineer, and I was going to be taught to fly by an old, long, tall drink of water named Bert Clory. Ran a little tiny 2,500-foot strip across the street in Dallas, Texas, from what is now Texas Instruments main building. And I recall him taking me by the hand at age 40 and walking me up to this J3 yellow Cub. It's ticking over by the side of the runway. And he says to me as follows. He says, "My son," he said, "this here's an airplane." I said, "I know that's an airplane." He said, "Shut up." And from then on, we understood each other. Look, the guy had a thick spiel to go through. For him to omit something, presuming I already knew it, might well get me killed. Is that a fair statement? The other thing is that what he figured, what I thought I understood about that airplane might be absolutely and diametrically wrong. So with that in mind, let's start from scratch. Static electricity, this is not so much designed to show you as it is to show you how to show somebody, because the main problem in the plant is explaining to the girl who is wearing that wrist strap that it is not designed so she shall not go for coffee. You know, most of them think it's slave labor. You got to be chained to the table. Okay, you have to know why. Static electricity to begin with is electricity which is not moving. That's what the word static means. We misuse the term a lot. Heard static in radio, right? What you heard was the RF pulse produced by the discharge of what had up to then been a static charge. Secondly, static is a surface phenomenon. No surface, no static, which is why pure gases don't generate it. It's the airborne particulate matter or the airborne droplets of moisture that touch and go. The separation of surfaces causes static charging. Does everyone understand that? Also, static is a first surface phenomenon in the fact that if you have anything which is charged, it charges on its external surface. How many of you guys have seen a Van de Graaff generator ball to which I bear a startling family resemblance? Now, you got to know that it doesn't make any difference whether it's a solid ball or a hollow ball, or as long as the outside of it is metallic, right? And the charge is, presuming it to be a negative, the electrons don't like each other. They get as far apart as possible. They're on the outside. Nothing happens inside that thing. Volume measurements have nothing whatsoever to do with the behavior of static electricity. Straightforward? Next move. Okay, but whenever two surfaces come together, no matter how lightly they touch, and even if they are apparently identical, triboelectric series be damned, there is no such thing as two surfaces which are totally identical. And as you peel them apart, presuming them both to be dry, one of those surfaces has a marked preference for electrons over the other. And as they are peeled apart, one surface will pluck electrons off the other, leaving that surface plus charge because it lost them. Does everyone understand? It's like two guys sit down at a poker table, one of them gets up rich. It don't come out even. It's always an interchange like that. Now, mind you, the easiest way to show it is with Scotch tape. When you unroll the stuff, the main roll plucks off electrons, leaving that becoming minus, and the piece becomes plus. It's a rather good mnemonic. Main roll minus, piece plus. In the case of the standard Scotch magic tape. However, if you switch to Permacell, which looks very much like it, it reverses the polarity. And I had a guy once rewire a static meter. He thought it lost its mind. Wrong tape. Okay, okay, understand how that works, right? Easiest way to show it, mind you, if both these surfaces have been conductive as they separated, this could have run right back home in the moment of separation and there would have been no charging. But if one surface, just one, is a relatively dry non-conductor, a rubber belt separating from a steel pulley, a man walking on a dry steel floor wearing Adidas will charge, okay? Well, the easiest way to show it, may I borrow your right hand, my lady, just like at rehearsal? Would you hold your hand there for just a minute? You form a very neutral ground because the outside of you is conductive, you know. And so when I unroll the Scotch tape, it comes off with a healthy plus charge and gets attracted to the lady, for which I don't blame it in the slightest. On the other hand, her touching it cannot possibly have grounded it because it's a non-conductor. The charge remains upon it. It would be attracted to the negatively charged surface it just left or to any other thing. Here comes another plus charge piece, and these two do not like each other. So they push each other apart with a startling amount of push because the charges are alike. See, likes repel, unlikes attract. It's like boy, boy, girl, girl, except in Hollywood. Now, mind you, as they're sitting there, they're slowly but surely attracting from the surrounding air the little airborne negative ions afloat in this room. Left alone long enough, they're pushing the plus ions away. They don't like them, but they're attracting negative ones. And slowly but surely it would be losing that repulsion. So anything left alone long enough will slowly but surely lose that. Okay, why things at rest don't generally have much on them. You can add to the populations of ions with air ionizers. How many of you have seen this one? This is the cheapest one. This is the little thing that's used to take the static off of records, as they say. When you squeeze this, there's a piezoelectric generator in there, and you produce a 25,000 volt corona, and on the squeeze you get a rush of plus ions, and nothing happens. That doesn't like plus ions. When you let go of it, you get a rush of negatives and a corresponding diminution in the repulsion. Does everybody see that? Okay, so from now on, everybody in all the workstations will stand there with one of these and do this at 60 hertz all day long and work with the, come on. In the first place, two things are wrong with that. One, the plastic had to have a charge on it first to invite the neutralizing ion over to neutralize it, right? See, secondly, if I'd left it alone long enough, it would have lost the charge anyway. And there's a third reason why you can't use one of those or shouldn't use one of those. Radios hear sparks. That goes back to some fellow named Marconi. I'm a little late getting here with the news, right? But the whole idea is that we have here the Anderson Effects ESD spark detector and shielding evaluator. We sell it for $895 to the unsuspecting. In an emergency, it serves as a 698 AM radio. I doubt if you guys can afford instrumentation of this sophistication, man. I mean, that's a little difficult. But you turn that up. Yeah, it's not bad. You know, it's off a station. Understand. Listen. How many of you guys think you ought to have a pulse-type ionizer located anywhere in the vicinity of a circuit board? Come on, man. Ridiculous. However, 3M has an answer to that. They put out for only $500 per table per year, they will furnish you a radioactive air ionizer, which doesn't make radio noise, and its entire job is to cause the slow collapse of those already charged plastics, okay? To take and neutralize the charge on them. Mind you, at $500 per table per year, it does a fairly good job of doing that. Unfortunately, generally, the static damage is done in the discharge damage is done in the first 100 nanoseconds if you're separating that tape, so it's a little late getting there. But it does, if you hold these tapes up in front of it, slowly cause their collapse, right? For only $500 per table per year. Send it back and get it reloaded every now and then. This is a cigarette lighter. It's considerably cheaper. That's the Anderson air ionizer. We sell them for $9,000 to the unsuspecting. So I have to know a little bit more about it than that. Look, ionization has its place. Okay, it does a lot of good things. It cleans the air superbly in a room, ionization by precipitating the dust. But the use of air ionizers generally to try to prevent ESD is a waste of time because of two things. The pulse types are actively dangerous near circuitry. And the radioactive types people don't like just because they don't like the word radioactive. And secondly, they're too slow because I can sit there and light neon bulbs buying rolling Scotch tape down the very throat of the world's best air ionizer. Okay? Understand. So, ionization. Oh, anybody care to guess how much charge was on the tape simply because I separated it? Mind you, I didn't have to rub two Boy Scouts together. How many of you know the word triboelectric is based on the Greek word to rub, and people think you had to rub things to get chest. But rubbing things just multiplies the numbers of contacts and separations, right? And the more times you kiss and get off, the greater the charge. It works that way, okay? Everybody see that? Not necessary to do it. When you want to measure how many of you guys have seen static meters? Let's see hands. Anybody seen static? How many of you seen the big pistol? You know, the one that looks like a flare gun? 3M makes a very good one, or it's made by an outfit called Sweeney in Denver. Sold by 3M, but it has a radioactive sensor in the front. Looks like a 4-pound flare gun. And where the hammer of the gun would be, there's a 3-scale meter. In the front, there are 3 apertures to control its sensitivity. Behind the front muzzle, there's a little titanium disc. And because they thought in the early days one had to ionize the absorptive area, it has absorbed to that some 200 millicuries of tritium, or hydrogen-3. So the gun has to be and is marked radioactive. Did you ever try to walk on an airplane with a 4-pound pistol marked radioactive? I mean, they take a dim view of that. So some years ago, we designed it down to about this size, took the radioactivity out of it, and colored it a somewhat nationalistic pink. This is the Anderson meter. There are many of them on the market. This is not a plug. It's a financial pleasure to specify this one. But the interesting thing is it's built like a Sherman tank. And if anything happens to that, including you're running over it with a forklift, you phone us the number, we'll send you another one. However, you are expected to change the batteries now and then if it's an electronic genius somewhere in your plant. That's it. Could I get you to hold this in your right hand, my lady, just for a moment? These are all calibrated at the factory by pointing them at the center of a square foot of metal sheet hung 6 inches from the sensor in a Faraday cage, which is a wire screen structure in which radios cease to receive. May I see the hands of anyone in this audience that believes radios play in a Faraday cage? Thank you. Bear that in mind. Notice there's nothing on the tape until I separate it, but when I separate, that becomes plus and that becomes minus by several thousand volts, right? Everybody see that? Now, if you can't afford one of the, the head of the physics department at Jet Propulsion Laboratories is by no means stupid. Okay? The man did not reach his stage in life by being stupid. But I promise you hand the man his first static meter, he turns it on and centers it, points it at his other hand, does this, says, summer gun doesn't work. And then the sucker light comes on, man. If that works, you have an artificial arm. See, your hands are electrically alike because they're connected by the sweat layer on the outside of your body, which is highly conductive, and that's where the static charge was anyway. If that were not true, you could zap your own nose. And isn't it fortunate you can't do that? Otherwise, you reach for your ear, you would knock the whey out of yourself, right? And I can think of conditions. Well, never mind. Okay. Now, now, good Lord arranged it so you can't zap your own nose. Would the lady hold that in your left hand rather high so the camera can possibly see that? And notice that if I move my foot, I'm bringing it up onto my skin, and it's showing you what comes on my hand. May I have your other hand? Notice that when I'm holding the lady's hand, I can't do it because we have connected our sweat layers, which can be fun, I've often said. Okay, does everybody understand that? You can also check that sweat layer out by using one of these little things, which is called a zap flash. How many of you guys have seen one of these? This is a small continuity tester, 2 bipolar transistors in the Darlington configuration, 3 1.5 volt N cells, and a GE48 incandescent bulb. So that if I hold it at the naked case point, which is right down there by the top, and hold it with my other hand, I'm using my sweat layer as a conduit. Would the lady hold that between the fingers, okay? May I have your other hand, the free hand or the one that's reasonable? Look. We have connected our sweat layers again, right? Notice that if I touch the lady's fingernail only, it does not light because the fingernail does not sweat, and this does, right? You're sweating a little more than usual right now, aren't you? Look, you want to hold that rather still? Look, the back of her hand is reasonably dry, as is the back of mine. So when I come down on this with a small individual touch, there's not much to do it. If I increase the area of contact or go all the way around, I get a much better ground. Does everyone understand that? Very simple way to check it. All righty. So in the real-life work of static electricity, this is to find your rugs, or the things that charge, and this is to find the doorknobs, or the things that can make the spark. Does everyone understand? These are the two base tools. All righty. If you can't afford an Anderson static meter, there is a simpler and cheaper way. I'm about to make an ash of myself. My lady, would you stick your left hand out this way? Just hold that for like a small table for me. What a nice lady. Look at here. You make an ash of myself. That's one of the reasons we smoke. This is the poor man's static meter. When you want to check one of these things, you want to find out, you bring the test material 1 inch above the pile of dry cigarette ashes and do this, right? And if those ashes leap up as they did there to coat the surface of that tape, you have a minimum charge of 4,000 volts on the surface of that tape. Mind you, that's 4,000 plus on the piece that unrolled, 4,000 minus on the surface from which it unrolled. So between those two surfaces is a minimum difference in potential of 8,000 volts. Looking for some place to happen, but we haven't had any sparks yet because we're still playing with non-conductors, right? The ladies have a problem with static cling. You know, the skirts that get affectionate. You know how that is. This is why that is. Now, this is your skirt, right? This is your substrate right there. Okay. As that separates, man, it wants to go home. So that clings to you, and every guy is familiar with that. Okay. But now, that's why the front of your CRT gathers dust. It has to have a plus charger. It could not very well attract the electron bombarding it from its rear. Right? Now, you've just seen static's entire repertory. Entire repertory, as long as it is just that, static. It can cause the attraction of something of an unlike charge, or the repulsion of something of a like charge, right? End quote. Therefore, there is no such thing as electrostatic damage. There is no such thing as an electrostatic sensitive component. They are sensitive to and they are damaged by electrostatic discharge. Okay? In short, it's not till that charge decides to go somewhere in the form of a fat little spark that you have any trouble with what? Setting fires, igniting explosives, burning your way through gate oxide in the little devices, or fogging film, any one of these things, right? In short, no spark, no damage. Would the class repeat after me? ESD is a spark, class. ESD is a spark. Man, if you get that in mind, you're way ahead of the average physicist, okay? They forget the doorknob half of the syndrome. Does everyone understand that? You do not make sparks with non-conductors, with exceptions that are too small to be statistically significant. Sparks occur between conductors, and there are only 3 of them. They are metal, like the doorknob in the wooden door, exposed metal, right? Any metal will make a spark if it's touched. Metallic carbon, which is the central pole of the dry cell, the arc of the light, the graphite of the pencil. Unfortunately, carbon comes 2 ways. It comes in when it's black, it comes in the amorphous form of the lamp black or soot, which conducts zilch. But for the purposes of our speech today, when we speak of carbon, we're speaking of the metallic form of it, the central pole of the dry cell, the arc of the light, the graphite of the pencil. And that is a metal, but the layman doesn't know that, so we say, all right, metal will make a spark, and metallic carbon, like the things that the black conductive foams and things are made with, will make a spark. The third thing that can make a spark is you. Because on the outside of your body, as we just demonstrated, is a highly conductive layer of salt water, which is highly conductive. Okay? Now, think of 3 things. Sparks are made by metal, carbon, and you. Okay? Now, let's look with what happens every day. I start walking across the floor, across the carpet. My non-conductive shoe sole, with every step, is peeling free of that carpet, a la that Scotch tape, right? So the sole of that dry Adidas is either picking up or dropping off electrons, depending on what I'm walking on, right? And the sole of that shoe now has 5,000 or 6,000 volts on it. But if I tried to zap this lady with a shoe, I wouldn't get very far. You're not likely to throw a spark with a non-conductor, not at these voltages, right? Next step is that the charge on that non-conductive shoe sole produces a field which induces some portion of that charge on the nearest conductor. You can only induce on a conductor. You're not likely to induce on a non-conductor, fair? And the nearest conductor is the sweaty sole of my foot. And now that field induces a charge on the outside of this Van de Graaff generator ball. The entire outside surface of my skin becomes highly charged, and then I start looking for somebody, right? And if I touch this lady on the nose, she would promptly give me a fat lip and instant retaliation because she knows karate and kung fu and several other Chinese words. Look, the point is I could cross this room for 30 years and not make spark zilch until I reach for one of 3 things. The doorknob in the wooden door over there, right, would accept that spark. Anything faced with exposed black metallic carbon would accept that spark. And the third thing that can accept that spark is somebody besides me, right? Can't happen to me because, unfortunately, I'm the same all over. Does everybody understand? All right. How many of you guys ever slid your tail across a vinyl seat cover on a winter day and kissed your girl and raised her morale considerably? Think of what it took to do that. 3 things. 1 dry non-conductor shall separate from something and produce a charge. That charge must then be induced on another conductor, namely you, and discharged at a second conductor, namely her. In short, for every instant of ESD, there are involved 3 things. 1 rug, 1 feller, 1 doorknob. Everybody got that? If I touch a doorknob, the doorknob will spark. The spark will be in proportion to the size of the surface of that metal doorknob. Okay? It doesn't make any difference whether that's solid metal or plastic plated with metal. The charge is strictly a surface phenomenon, and the spark is identically the same size. If I wanted the largest possible spark, I would ground the doorknob, giving me the world's entire earth as the acceptive target, the other half of that capacitor plate to accept that. You see, it will take everything I've got in a single shot. Everybody got that? All right. Now, all up to now was horseplay, but in 1964 there were no antistatic plastics. They had conductive plastics and they had non-conductive plastics. Their choice lay between get me a rug and get me a doorknob. And down at Cape Kennedy in 1964, there squatted on a spin test stand a Thor Delta 3rd stage solid propellant rocket mated to an orbiting solar observatory satellite. Mind you, the people who put that together were not dumb. No better scientists on tap. Finest telemetry have figured out to that point by the mind of man. Shoved up the tail of that thing in order to fire it was an igniter squib. Looked like this, an aluminum cylinder, a bridge wire like the filament of a light bulb, which will grow hot when you feed the current into that thing. Cuddled around that resistive or heatable filament is a wad of lead stiffnate, a first fire mix, much like the head of a match, going to burst into flame when you heat the filament. 15-second fuse, like the delay train on a hand grenade or the fuse on a firecracker. And the wad of tetril, an extremely brisant, sharp explosive, going to burst the squib, fire the solids, and send that thing in whichever direction it happens to be pointing. Now, since this is tied down on a spin test stand and a hangar full of technicians, NASA has no desire to feed current to that bridge wire inadvertently. So they called in the safety boys and the electrical engineers to do what engineering dictates, and they promptly do that. Make it safe. Dead short it, right? Twist the leads together so they cannot pick up broadcasts, and ground it. That's about as safe as electrical engineering in those days permits you to get. There is no conceivable way you can pass current through that bridge wire. It is twisted together, solidly grounded, and shielded by an aluminum cylinder. And hanging over the bird was a large polyethylene bag, a drape, a dust cover to keep that thing clean in a room where they fire you for the dust off a pencil point. And they rolled it back out of the way like you'd tuck up a skirt to walk through a mud puddle, made their adjustments to the complex spacecraft, pulled the tape loose, and permit that cover to unroll. And static is a function of area. And the simple unrolling of that cover generated on that falling curtain some 37,000 electrostatic volts. Now, that plastic curtain is not going to throw a spark, gentlemen. Plastics don't do that. What it does do is step two. It induces the charge on the nearest floating conductor, namely the shell of the squib. And that charged up metallic object is looking for another piece of metal, preferably a grounded one, makes the spark larger, at which it can discharge. Would one of you engineers care to point that one out? Zap, right through there. Tiny little spark. And 15 seconds later, the thing went off in place. It fried 3 engineers alive in their tracks. It put 11 men in the hospital, tore the laboratory and $55 million worth of spacecraft into absolutely unrecognizable junk. And all of a sudden, static electricity had stood up on its hind legs out of General Science 1 and said, fellas, take a look at what I can do. You got to know that what attracted somebody's attention. How do you brush that one under the rug? We had a minor disturbance in Hangar 3. Come on, the defecation struck the impeller. Out of the instant, there sprang a couple of requirements. One, let's learn how to short squibs. Pin to case. A simple solder joint. One, bridging that spark gap would have had you already holding hands with your girl, in which case you couldn't have thrown a spark at her, you see? Straightforward. Simply wasn't there because nobody among all these brilliant engineers had figured out what happens if you bring a plastic bag somewhere near an electronic device. Part of the scenery, been there for years, still is. The other requirement was let's have a cover we can safely bring into this clean room that will prevent the recurrence of that. Now, mind you, nobody won't do that again. First thing they thought of was the black conductive Velostat plastics. How many of you guys have seen those? That was and is a superb product. It was a black polyethylene, looked very much like the black polyethylene you have over your strawberries, which is maybe 2 or 3% amorphous carbon to cover its flaws and to make it black. This was 55% ground up battery poles and just enough polyethylene to hold the crystals together so that you had in effect an actual sheet of metal, both chemically and electrically, and it was excellent. It's a magnificent material for what it was designed for, which was powder plants. And a powder plant separating the conductive walls of that produced no charge whatever, right? Worked out real well. When you want to find out if that is black carbon, you take your trusty zap flash, check it from finger to finger, come down on that and touch that, and you see that's a conductor. It's a sheet of metal, both chemically and electrically. Does everyone see that so far? We'll wait to check it. When the time came to take that into Cape Kennedy, it had a couple of drawbacks. One, it was blacker than a yard up a chimney. You got a black bag full of dynamite caps and a pair of scissors, you're in deep yogurt. It'd be nice to know where they were before you started cutting into the bag. It would also be nice to know the nature or the condition of the packaged object, right? Secondly, if you rub that against something, and they actually had the experience, they covered the spacecraft in that. You notice that the paper is white. And when this was, you could literally write your name with that, okay? And every single fleck of that black carbon was a dead short to microelectronics. Right? You were raining conductive powder into them. Thirdly, if that was hanging over the drape and I took a step toward it and reached for it with my finger, there would be a small spark. And a $5 radio will hear that spark, right? Now, the antenna aboard that spacecraft could pick up your broadcast from 250 million miles out. That's a reasonably sensitive receiver. What you don't want in that room is a spark, man. Your data's binary. Straightforward. So, they threw that out. Oh, one other thing. Carbon was the central pole of a dry cell. It is a metal. And they had an experience by putting that over the first surface metallization of an emissivity shield. but had finely divided aluminum on it, came back in 3 days and took the cover off, and the metal beneath it had vanished. It forms a 3-volt battery and quietly eats the metal off, right? Now, you guys could laugh, but how many of you guys have seen the black conductive foams that are consistently marketed to stick the leads of devices into to dead short them, right? Okay, both the British Ministry of Defense and Sandia Laboratories found out that you jam leads into those things, it not only corrodes the leads, it removes them entirely given time. I mean, there's not an engineer in this room that would have jammed those leads into copper mesh and stored them. You just said to yourself, that's a dissimilar metal. So is the carbon, both chemically and electrically, but it still exists. Okay, so they threw carbon out in 1964. You couldn't use it. Next thing they thought of was metallization. Vacuum. How many of you folks have been in a motel, had a mirror on the ceiling so you can shave in bed? You know, the first time I saw one, I thought I was being attacked by a naked skydiver. Ugly brute, as a matter of fact. You got to remember, that was a plate glass mirror, and it fell on you. It could spoil your entire evening, or in effect, cut it short. So this is usually a piece of this. This is metallized mylar. You know how they make that. They run a roll of mylar, roll to roll, in a huge vacuum chamber with a pump on it big enough to keep up with the leaks at the door, because it's a fair-sized door. First pass out gases that and boils off its impurities. As it's rolling back, you have a trough of molten metal underneath it, in this case aluminum. You know, and the aluminum comes out silver. In the case of 3M's so-called static shielding bag, that's nickel, kind of a bluish color, but that deposits there. And it looks to the naked eye rather like a mirror. To the microscope, it looks like popcorn on flypaper. You know? And the way you can tell that's not a solid sheet of metal, which it strongly resembles, is if I put this over the gentleman's eyes, he will attest that you can see through that. All right? That's how they make the cop glasses and the one-way mirrors and stuff like that. And if you reflect for a moment, you realize you're not seeing through metal, you're seeing between the dots. You see? So, incidentally, every time that's flexed or abraded, it's raining, guess what? Aluminum powder into your circuitry, right? Secondly, if I touch this, I make a spark, right? If I make a bag by having the metal on the outside and taking 2 sheets of this and sticking the plastic sides together, I've just made the world's largest capacitor, right? Whose job it is to store the static charge and deliver it in a large and destructive sparky lump when you connect those 2 plates, right? So they threw these out. That left us with one. There went metal, there went carbon, the 2 of the 3 conductors, right? The only one left is water. And there's always a guy in the audience that says, wait a minute, Anderson, water does not conduct electricity. And the man is right. If you can find me some that is totally and absolutely pure. My answer to that is find me some. You know, all the water you will ever see has been exposed to air and therefore has a little CO2 dissolved in it at best and becomes dilute Perrier. So it conducts. All the water you will ever see conducts electricity. Those of you that doubt that are invited to stand in your bathtub and reach for 220. You know, I lose more objectors that way. Okay, you have to think practical. Trouble is, plastics don't want to get wet. Polyethylene, after all, is like a candle wax, like the wax surface of your car or the greasy surface of your plate. How many of you have noticed that when it gets wet, polyethylene water beads up on such surfaces in the form of little separable hemispheres, right? Now, droplets like that are present on all surfaces at all relative humidities short of 0, but the size and the number of those droplets reflects the wetness of the atmosphere, the relative humidity. On a dry day, they don't touch each other. There's no leakage path. On a wet day, you get bigger drops and more of them, and it begins to look like a sweat layer, right? Mind you, it's missing one thing. It hasn't got your salt, so it is not conductive enough to spark on contact. If you touch such a surface, the charge from the charged object comes off approaching 0 asymptotically like that, like sliding down a banister. Whereas touching a conductor does it very fast and in the very spark you do not wish to have. Does everyone understand that? This damps it. So they're called static dissipative or antistatic surfaces. Everybody follow that? However, what that water on a surface will do is to prevent charging entirely. Presume that when I separated those 2 surfaces, one of them, just one, had been evenly, microscopically, non-corrosively, and permanently wet. As you separate them, you form a layer of water between these surfaces, and the electron that I pluck off runs home in the moment of separation to the point it just left, and there is no charging. This is why you can't get static by stroking a wet cat. I have tried it repeatedly, no luck whatever. How many of you guys have stuck your hand in the dryer at home, you know, the clothes dryer, and the hair prickles up on the back of your hand? Take the clothes out. You will get no signal if even slightly moist. Ever understood? How many of you have heard that you don't get zapped as much when the humidity is up, right? And people say, well, that's because the air is wet, and wet air is a good conductor. Wrong. Wet air is a slightly better insulator than dry air. It's a physical fact. And if you think wet air handles static, go watch a thunderstorm. No, the reason you use, a lot of people say, why don't we run the plant at 100% relative humidity at all times? That's going to suppress this, and that's right. It's rather like saying the best way to get rid of enemy submarines is to boil the ocean. See, above 50% you can't work for sweating into the work. Above 60% corrosion is guaranteed, right? And the only reason you needed to wet the air was not to wet the air, but to wet the surfaces, right? Now, a lot of easier ways to wet surfaces. What we discovered a long time ago was you could take a piece of polyethylene and dip it in a topical antistat, which is like a detergent, like they call surfactants, antistats, wetting agents. They all have in common one thing. One end of that molecule likes oil, the other one likes water. And you leave a trace of that on the surface, and instead of getting the droplets, you get an even, dropless, invisible film of water bound chemically to that surface, and that will remain there at 0 relative humidity because it takes an oven or a vacuum to drive that free. Right? Incidentally, this is why your dishes drain droplessly dry after being dipped in the cascade, and while the kids at college are drinking Windex, it keeps them from streaking. That is the worst joke in this whole series, but I can think of nothing else that fits this thing. Okay, everybody follow that? Okay, but sooner or later, that tiny little trace of antistat in there, which is not conductive, it simply holds water, which is going to be leached off, abraded away, somehow gone, and it must be replaced. And there are antistats that range from the downy fabric softener that you put in to keep the pantyhose from getting affectionate, and it lasts for 3 or 4 days till you wash them again. Then there are things like rescue, staticide, long-term ones that will last 6 months or a year before they need renewal, but the best of them must be renewed sooner or later. Is that understood? What we discovered in 1964 was that you could cram a concentrated form of one of those migratory antistats into the polyethylene, and it requires very little to do it. And over a measured 20 years, it would keep migrating to the surface and, in effect, redipping the plastic in fresh antistat. Does everyone understand how that works? And by doing that, Richmond created the first antistatic polyethylene, which was called, and this is not a plug, it's an explanation, was called RCAS 1200. Stood for Richmond Corporation Antistatic, and my birthday was the 12th, and the 100 made it look like a bigger act in 1966. And it left room for modifications like 1201, 1202, which thank God we didn't have to until recently to make, because as soon as we changed 1 iota of that, NASA would like a 19-year-old sample, you know, to make sure it kept that up. Anyway, originally it had no color, so we decided it looked like anybody else's polyethylene, and only with a static meter could you realize that it was not charging. It would not light it was not conductive enough to light a zap flash, so people said, man, that's not conductive. Yes, it was, but just slightly so. And the other thing was that when you took a static meter and charged it up and did this for 20 minutes, man, it would not move the meter. Simply did not charge. Whereas the standard things that one runs into, just for fun, how many of you guys carry the instructions on how to keep the place free of static around in an envelope like that, you know? Okay? It's standard. They're part of the scenery. You better learn that they're there. Okay. So, immediately was snapped up, and they said, would you identify this for us by printing on it with conductive ink? This is RCAS 1200. Really, it is, fellas. We said, wait a minute, man, that ink would have produced a spark if you reached for it. Remember? Small though it was. Secondly, it would shed metallic ink, or conductive ink and dear stuff. So we said we wouldn't do it. The guy said, all right, well, color it for us. We said, what color? The guy said, red for safety. We're going to drape the Saturn V and make the world's largest phallic symbol. And we said, no, if we did that, it would make it opaque and you couldn't see what's in it. You have the black bag full of dynamite caps again. Huh? So we backed off on the intensity of the red, and we ended up pink. And that miserable pink color has haunted me for something like 20 years. Of all the sexy colors for an industrial use, man, that belongs in a nursery or a bedroom, any way you play that. The guy that introduced me at Rockwell when we draped the first spacecraft in that says, Anderson, I don't care what they say about your color, I think it's darling. You know, you get a lot of that. The funny thing is that turned out to be like falling in the sewer and coming up with the crown jewels. Pink is an unusual color in an industrial atmosphere, given, right? You walk aboard a battleship and something is pink, you either worry about the crew or you figure that's pink for a damn good reason, right? So it turns out that's the color for it has become picked up as the flag for antistatics. Does everyone understand that? Okay, that's where it came out. I'm kind of proud of that, but it's interesting. Unfortunately, we have no monopoly on the color pink, so as soon as this became a financial pleasure, everybody that could throw pink color into polyethylene, and sometimes an antistatic, sometimes not even that, was making pink poly. Okay? But it is a good material, and it's a good way to know how to do that, but at least know who made yours. Okay? We're now required by the government to stamp our names colorlessly into every one of these military bags because of the bad, how would you say, the growth of the imitators on the field with no background history. Everybody understand that? Okay. Now, so that was originally immediately snapped up at Cape Kennedy and has been used to drape every spacecraft that's flown in the past 12 years, has been, or 20 years, has been covered with that or its first cousin, which is an antistatic nylon we make called RCAS 2400 because it costs twice as much. You know? We have a complex way of naming things. Nobody in those days knew, however, that they were damaging electronics. Their interest lay in not attracting dust nor setting off explosives. That's all they knew about. They did not know they were hurting electronics because in 1964, radio solid state was just getting off the ground. They were still using radio tubes or what the British call valves, which is a better term. Anyway, there were two reasons why they didn't know. First, the things they were working with weren't so sensitive. And secondly, if you had an explosive device like that igniter squib and you got a plastic bag near it and it did that, you were pretty well aware that something, I hated to wake you, you're pretty well aware that something had gone wrong. I mean, nobody in this room missed that, right? You had a visible sign, an audible signal, a tactile sensation. It took your hand off, it attracted your undivided amoeba. Now, the time and the place of that failure were not only clear, they were flat spectacular. Okay, at my age, I have these hot flashes. I don't know what caused them. However, I had a full head of hair before I started doing these shows. However, the electronic devices that you guys deal with, the ROMs, the PROMs, the CMOS, the MOSFETs, and all those weird initials in which you guys are wont to communicate, is that they don't do you any such favor as that. How many of you have seen the innards of those things blown up to the size of the wall over there? It's still hard to see the map of Sydney, Australia, and some of those complex circuits, man. Thousands of little connections. No matter how complex they be, no matter how fancy, there lurks within them at least one configuration and sometimes thousands that you might simplify as follows. Here is a conductor, and here is another conductor, and between these there is a layer of what? Gate oxide, glass, insulator, right? Incidentally, at this magnification, you would be roughly 6 million feet tall. These things are small. However, leading up to this thing, there is a lead of some kind, or it could not function. Fair? Now, two things can happen. Here I come, I walk around the laboratory, I put my foot is separating from the floor, I generate 1,000 volts on my shoe sole. Of that, perhaps 90 comes up on my skin. I can't have it all. And then I reach out and I touch that lead with me or with metal or with carbon, any one of the three. And instantaneously, I have 90 volts here and nothing here, right? The alternative is, suppose I don't touch it at all. I'm not even going to touch it. But just like that shoe was near my foot, like that drape was near the squib, I bring a plastic bag of the instructions on how to keep the place free of static somewhere near that lead, and there's 5,000 volts on the plastic bag. And it gets induced on that antenna, and in either case, I've got 90 volts here and nothing here, and what happens is, patooey! And a small spark goes ripping from this conductor to that conductor through the intervening gate oxide in something under 100 nanoseconds, 100 thousandths of a millionth of a second. That is SR, that is startling rapidity. That is micro lightning. It gets incredibly hot in there. There is no time for heat dissipation in that duration of time. And you melt a physical hole through the glass, and you vaporize the metal, right? And the metal vapor does the mirror on the ceiling bit. And as it cools out, it coats the walls of that hole, and we have here a dead short, and the curved trace says, tilt, bring me another one. That one, like Hemingway said, died well. It's all over, man, in less than 100 billionths of a second. Now, If that happened to all of them, at least when that one doesn't get out of the plant, QC would catch that one, right? If it ran that ship through every possible combination within its repertoire, it would find that. However, it's been estimated that that happens to less than 15% of them that receive ESD damage. To the vast majority of them, something else happens, and let's do it like the British say, "Sime again." Conductor, conductor, right? This time, the antenna is a bit shorter. This time, the humidity was up a trifle. This time, I took one less step on the floor. This time, the plastic bag wasn't quite so large or quite so close or quite so recently moved. Any one of these factors. And we end up with 80 volts instead of 90 over here. And what happens is patooey, and the spark goes through. And this time, the metal vapor stops perhaps halfway down the walls of that hole. And that device, ladies and gentlemen, is pregnant. It is carrying a failure around with it. It just hasn't given birth to it yet. Unfortunately, that will pass every test in your house with highly acceptable, if slightly atypical test results. It works. It functions. And then 3 days later, 3 months later, in a 3,000-mile orbit, or as you press the button to leave the moon's surface, that thing throws up its little feet inexplicably and dies. How many of you guys have said to yourself, "It was all right when it left here"? Didn't happen on my watch, Captain. Come on. It took NASA 8 years to find that. The reason's fairly simple. You can only see that damage under a scanning electron microscope at 4,000 diameters, $2,000 a look, and you don't get the device back. Now, who's going to do that? It's totally impossible to do that. It happened for one reason, gentlemen, because there was a spark, man. It boils down to no spark, no damage, right? So to use materials capable of making sparks to try to prevent the production of sparks is axiomatically suicidal. Does that make any sense? All righty. First guy that caught on to that was with resistors. How many of you guys know what a resistor is? I used to think a resistor was a shy girl. I didn't know anything about that. Look, I still don't claim to know anything about electronics, but when I was going to school, resistors looked like this. Here's a cylinder, usually of carbon, with a couple of leads stuck out of it, you know, and plus or minus 10%, plus or minus 5 if they got gold on them. Them are expensive kind, right? You could buy them at Allied or Lafayette. Tandy or Radio Shack was still making leather in those days. Anyway, they were plus or minus 5%, you know, but in the modern world, that's far too crude and the carbon has to go, and this becomes ceramic, which conducts zilch, right? Then they do the mirror on the ceiling bit and coat that ceramic with the metal powder, right? And then they get in here with a micro lathe and cut that away into a precise helix of metallization, which is give or take 0.1%, man. Reliable as the laws of God, plus or minus 0.1% tolerance. And in 1968, there was an outfit called Standard Electric Lawrence in Stuttgart, Germany, building a spacecraft. Required 5,000 precision resistors, 20th watt, 1 kilo ohm, 0.1% tolerance. They ordered them through TRW, who had them made up by an outfit called Ingstrom Corporation in Van Nuys, California. Everybody know about Van Nuys? Named by an Italian explorer. Somebody tapped him on the shoulder and said, "What do you think of the valley?" I said, "Van Nuys, Van Nuys." Anyway, they made them up and they measured them accurately on the Kelvin Bridge, which I understand is a Wheatstone bridge with an education. Anyway, they shipped them to TRW in little paper envelopes like pills come in, right? And TRW took them out and repeated the check. And every one of them was right on the money, man. And these guys are grinning like skunks eating beans. Everything is going fine. Now, I want you guys to repeat after me. Paper and cotton and wood, class. Paper and cotton and wood. Forget them. At the speeds at which you can move any one of these, you are not about to produce electrostatic discharge damage with them. When you wipe something off with Kleenex or a cotton swab, forget it. The ladies know you don't have to put Downy fabric softener in cotton. It's the spun plastics that tend to get affectionate, fair? The girls who work in powder plants are required to wear cotton undies. You come in here in nylon, honey, you can kill us all. I remember the inspector who was checking for that was pulling down $500 a month. But she hadn't had the job all that long, you understand? Anyway, everybody understand that. Now, you guys remember that, because there are people that go out and take a perfectly innocent corrugated carton that couldn't hurt you in a million years and coat it with black conductive lacquer, making a spark-producing doorknob out of it, and they charge you a premium for the privilege. Okay? Think about it. All righty. Next thing. So these things reach TRW fine in their paper envelopes, but TRW knew what you know, and that is you don't take a paper envelope into a clean room, it sheds inadmissible fibers, right? So right away they dropped each one of these in a small, clean polyethylene bag, and they shipped them by air to Germany. When they got there, Germany took them out and repeated the check on the Kelvin Bridge and wired back something like "Was hier los?" 119 of these 5,000 resistors had quietly and mysteriously shifted in value by as much as 6%. This was 60 times beyond the permissible tolerance. And once more, the defecation struck the impeller, and they shipped them back. TRW in 1968 went into an analysis that would boggle the mind, man. They put them through high temperature, low temperature, high altitude, low altitude, shock, vibration, thermal overload. They simulated the vibrations of the specific aircraft engines used in the shipment. They haven't moved a resistor yet. They sat there and sneered at them. 3 months into the study, the chief engineer of Richmond Corporation is a man named Ed Bowling. And he was married to a lady named Cheryl, who sold real estate or something, had no scientific background, whatever. And he tells on himself that she was sitting beside him one night having coffee. And as they were having their coffee, she piped up. She said, "I bet it's the plastic bags." Gentlemen, there is nothing worse than having your wife right. You know, when the entire crowd heads of your company can't tell it. You know, he says, "Honey, bring me another cup of coffee. Let's talk about something you're competent to discuss," right? But that lady, people accuse me of being an MCP for that. I'm not. That lady's single remark changed the world, gentlemen. She is responsible basically for 99% of what you're doing today to protect the ESD parts. Because that man went back to the laboratory and tried it, which is the thing to do. You know, don't theorize yourself into a spasm. He went back to the laboratory, procured a plastic bag. Mind you, he hadn't seen one. He'd shipped them in paper. He took precision resistor A, fresh off a Kelvin Bridge B, dropped it in a polyethylene bag, and brushed it with a sheet of paper for 10 seconds, simulating the shipment with paper separator strips. And as that thing, it took it out of the bag and noted that it was 20% different in resistance than it had been 10 seconds ago. He proceeded by that technique to blow every resistor of his manufacture, still hadn't told TRW, and went out and procured competitive resistors from everybody else that made them in the range. And as soon as he found out it happened to everybody's and not just his, then he told them. Does that strike a familiar note? Look, as that bag is rubbing together, it's kissing and getting off. You come off with 5,000 plus on this side, 5,000 minus there, 5,000 plus over here, 5,000 minus here. You have, in effect, a dipole antenna in that thing. This snuggles up against a plus, right? Guess what gets induced on it? This other feller over here snuggles up against that and gets the opposite charge induced on it. And those two massive conductors spit their sparks at each other through that intervening metal layer. Does everyone understand see that? Generally, it fuses two of those crystals together and drops the resistance, but because it is lightning, it occasionally knocks a crystal free and the resistance goes up. But in 100% of the cases, there was a shift, okay? Now, I was sitting in TRW's lunchroom in 1968 next to a room full of pink polyethylene. How many of you guys have seen the astronaut feeding bags on the Tang commercials, the things the guys eat out of? I had the pleasure of designing them in 1962, and I'm quite proud of that. I like having your chewing gum on the moon. However, it's also scarcely a volume usage. Greyhound bus had no use for them, whatever, okay? And if you think feeding the astronaut is the entire problem, you've reached an erroneous conclusion. At any rate, we were also concerned with exits and effluents. So there are not many of them sold, but they're prestigious. And the same thing was true of pink poly. We were in 1968 the only manufacturers thereof, and there was not much market for it. You simply used it for spacecraft and for explosive applications. And then this happened. And I was sitting in TRW's lunchroom in 1968 next door to a room full of spacecraft pink poly. And I heard these guys breaking up over the wife story, and I turned to this guy and said, "What in the world is a Kelvin Bridge?" And the guy told me. So I went tearing over to visit Mr. Bowling, and we sat at his desk in 1968, blew resistors all afternoon. How many of you guys believed this in 1968? Okay. The next thing we did, well, I went back to the plant and brought him every known plastic bag. We thought maybe that shift would be proportional to the zap. What a beautiful way of checking it, you know. Maybe if you hit it with 5K, you got a 5% shift. 10K, you got a 10% shift. No. But it's an interesting thought. Anyway, we were playing with it. And in the course of that, I threw him a pink polyethylene bag, and the thing did not move, and the man's eyes grew large. It was statistically staggering in a run like that. Every other common plastic had blown them. And all of a sudden, we realized there was a bigger market for this than was then known, and that's when it began. Next guy they caught on to it was Santa Barbara Research Institute up at, put this in your gun, gentlemen. For practical purposes, a circuit board or a component wrapped up in 6 mils of a good antistatic polyethylene, such as Richmond, has never been known to be zapped, not in real life. It is possible to do it if you make a deliberate, concerted, contrived effort to do it, okay? But in real life, there's never been such one report of such damage. However, first guy that caught on to that was, so we presume that anything in a pink poly bag or a static shielding bag is un-zappable, because they are. So down here comes a guy at Santa Barbara Research building a spacecraft with 500 circuit board supply 5. They're working in a 40% relative humidity. The guy's in these nylon bunny suits wearing Adidas, right? This is a stainless steel tabletop. You want a conductive tabletop? How conductive can you get? Now, how do you probe a circuit board on a stainless steel tabletop? You know, it's kind of interesting. So they used to cover it with a nice piece of white styrofoam, you know. Have you ever seen white styrofoam pellets, you know, that they ship the stuff in, they cling to the walls, the floors, the ceilings, and the cat? And if it takes 4,000 volts to lift cigarette ashes 1 inch, what do you figure on that stuff? How many of you have seen it pink? Okay, they dip those in antistats, and they become perfectly safe. They don't do a darn thing. And they put the pink in there so you know they dipped it. Otherwise, it looks just like the one that'll kill you. Okay, so the first thing these guys did was to cover up that stupid tabletop, which is a sparker. Ever see, if he moves his foot, it charges him. He spits his spark right through the device into that acceptive tabletop ground, right? Every time he touches it, there wasn't a ground strap, there wasn't anything. First thing they did was to cover up the tabletop with a piece of pink polyethylene, which is what led to their antistatic or static dissipative tabletops nowadays. Okay, the metal is buried. Everybody see that? The metal is not touchable because the first contact between any two metals produces a spark. Okay, next thing, they ran a wire from this guy's naked skin and attached his skin to that of the tabletop. Now he and his girl are holding hands, and with that simple connection, all the requirements for conductive floors, conductive shoes, conductive seat covers, and air ionizers and earth grounds going 8 feet down into bedrock went down the drain, because this man can stand on a Van de Graaff generator and he and the table are the same, right? No possibility of spark. However, there was a problem. This is not grounded. The man that does an energetic war dance here can charge himself and the table to 5K each, right? There's no spark between them, but if he touches any metal or any other person not part of that system, there is a spark. And the name of this game is There Shall Be No Spark. So they said, let's ground the fellow. And they took the guy's skin to the ground. Now this guy's attached to the earth, and he's standing here doing this, trying to alter the polarity of the world. Now his skin is going to be zilch. However, originally this was just a wire. You got that man hard grounded. He's standing there with his feet in the water, reaching for 220 with the other hand. Spoiled your whole day. So by OSHA requirement, you remember OSHA, our Savior has arrived? We began to build wrist straps, resistors into all the wrist straps. How many of you guys seen wrist straps? Okay, all different kinds. First one was an old piece of black Velostat, you know. Had some resistance, but if it fell across the power supply, it blew it in half. So they learned to insulate that doorknob. You know, it's not exposed metal. So they began to come out with coil cords, things like that. All different kinds. They had all different kinds of wrist terminations. How many of you have seen the... they had a bead chain for a while. You know, little guys would put a bead chain around the wrist and it made good contact, but somebody pointed out it was intermittent if you jiggled it, and it is. It's intermittent for 1 nanosecond. How much you think you can store in that length of time? But nevertheless, they didn't like that for several reasons. Then they went to one that was designed called the Fred strap by Fred Mickinen of Honeywell. He's a Fred Mickinen's thing. It was like a Spidell band that would grab your wrist all around. Called a Fred strap because Fred designed it. We have one designed by a Frenchman named Jacques. We don't talk about a lot. But there are a number of them. At any rate, nowadays, the trouble with that was open exposed metal on its outside. Any of you guys ever have the experience of laying a finger ring across a 6-volt car battery? You know what happens? It turns white hot on your hands. You know what you do? You fry your mouth. It's what you do. You haven't got time to think that one over. You shove that white hot ring in your mouth. I got the scars to prove that one. Look, so we learned to paint the doorknob. See, the outside of a conductor, of a wrist strap, shall be conductive, and its entire inside periphery should be. You see what I mean? There are many of them on the market that depend strictly on the contact of a little metal button up against your skin, right? And that is not a good ground. The way you can check these things out, oh, this is a new one. This is one I designed a while back. It's called the clean cuff. This doesn't have any stretchability to it. It's made of spring stainless. The outside of it is lacquered, so you have it protected on the outside. But that fits Vietnamese anorectics or Arnold Schwarzenegger, because you adjust it like that by twisting it, you know, that it fits you, and it goes on. And it's highly cleanable, whereas a lot of the straps, which are otherwise very, very good, are not too good for clean rooms because they tend to shed particulate. You know, any cloth-bearing thing. And there have been some where the buried wire in a cloth wrist strap have come loose and caused actual shorts or guide-up alerts on that. This is one with a good cloth band on it. Notice when you want to check it, you take your roach clip here on this end, or banana plug that fits into that thing, and you grab the end of your zap flash with it. Notice that if I hold that on its outside, it is not conductive, nor should it be, right? On the inside, if I touch that anywhere around its internal periphery, I light that thing. And that means that's a good ground all the way around the skin. Does everybody see that? You can also improve that conductivity by putting a little hand lotion on the skin. Pick a good one. All righty, so, when you issue the ground straps, there are two ways. The girls always react, this is, you've got me chained to the table. The worst offenders are the test engineers. I know how this works. I don't have to wear that stupid strap. How many of you guys heard that? Look, the lady that puts that ground strap on is vice president in charge of her table. And if the chairman of the board walks down that aisle and reaches out for something on that lady's table, she should hand him the wrong end of the soldering iron. He's got 100 nanoseconds to get his pinky off of that circuit board, man. And if you move that fast, you're the fastest gun in the FB1. Okay, there are no exceptions. Everybody got to put them on. We tell the engineers, well, I had an old fellow working for me one time cut through a 220-volt power cable with a pair of garden shears, and he lit up the general area pretty well. We were picking him up off the grass. We said, man, don't you know better than that? The guy said, well, boss, thought I'd cut through it right fast and let go before the juice got there. Now, that's a quote, but any one of you guys who thinks he can get his finger off a circuit board in 100 nanoseconds is in that man's mental category. There aren't any exceptions. The other thing is, when you are not working on them, wrap them up in a pink bag or a static shielding bag or something. Surround them so that the casual pinky of the walker by cannot touch them. Okay, I've walked through more plants than any other cotton pickers going to live long enough to in search of rugs and doorknobs. And I promise you, I have never gone into a plant where I could not physically reach out and touch a circuit board. And neither have you. Fair enough? Now, for a 5-cent pink bag around that, or a static shielding bag, would have protected that against all comers. The only time you undress those things is when they're actively being worked on. Is that straightforward? And it costs nothing to protect them. So do that. Surround. Now, put them in a cardboard box. Anything except a conductive one. Don't let them touch a conductor, because that spits the spark. Is that straightforward? All righty. Now, signs came out. How many of you guys seen signs like this? You see signs that came out for the girls? Caution! Static can damage components. Wrong. Static discharge can damage components, right? Do not handle unless the wrist strap is worn. Somebody at IBM got up and said, what if the wrist strap is new? You got to think about something. How many of you guys been in a motel where the sign out front says, no pets allowed except seeing eye dogs, right? Think about it. Who is that for? The man can't see and the dog can't read. The sign in my motel over here said, please place curtain inside tub before using shower. I did that. Took me 20 minutes to get off them little hooks, but I did that. You go in a plant, you see signs say employees only. Never says whose. You got a job, go in. Let me show you. When you want to show them how a wrist strap works, you take a girl in the dark room where I do my best work, and you hand her one of these things, or just a simple Ne2 neon bulb. Have you guys seen Ne2 neon bulbs? Simplest, stupid little thing in the world. It lights up with a discharge of 90 volts, 25th of a watt. And if this lady's holding one and I walk across this carpet and touch it, that thing will flash once, right? And the nearby radio cracks once, right? Meaning your finger is a single shot. Repeat after me, class. My finger is a single shot. Once again, My finger is a single shot. Good. You get one zap per nose, one zap per doorknob, got to reload to fire another. Okay? Now, trouble with plastics is they aren't single shots. Take a look at this. Stay with me a minute. I talk to each other while I find this stupid little radio. We're in a shielded building, so the radio's not picking up anything. Outside, you could pick up CBS, right? And you drop that in any transparent bag, including the so-called static shielding bags, you know, they're supposed to stop everything, and they play with undiminished volume. They are not shields nor Faraday cages. They are spark diverters. Okay? Is that straightforward? If the lady will hold that for a moment, and you take the little neon bulb and spread its leads out. We did this in 1968. This is called the Anderson effect. I'm writing this book entitled How to Be Humble, Though Great. Subtitle, Presidents Who Have Known Me, you know, which is Elizabeth Ray's line. I don't know why I'm using it. Look, these things are spread out right and left, the little leads are. Now that would simulate a device afloat in a plastic bag. I can't touch it, you can't touch it. The thing is totally insulated. And you notice that as I unroll the tape near that radio, there is no sound in the radio because, first off, the plastic don't make sparks. If you jerked it fast enough, you could get a tiny discharge. However, I want you to count the sparks as I unroll or separate this plastic and watch that bulb. In these lights, you can't see it, but it's going to light up like a Christmas tree, and count the sparks. See, not one spark went through that. Several 100,000 of them went through that, right? Meaning that the plastics that get ignored on your tables, you know, you've got a plastic bag full of nuts and bolts on the table, and you say, nuts and bolts are not sensitive. They are not, but the girl dumps those and waves that bag past your circuit board and quietly and silently destroys it. How many of you have seen the bubble caps that look like this, you know, except they're white? Great toy for vice presidents. We can pop the bubbles, right? By the hour. Urethane foam. You do that with a static meter and approach that to a white one, and it pegs the meter from quite some distance. Pink ones don't move them at all. And the reason there are pink ones is that there shall be no more white ones, but you guys have not made a physical effort to get rid of them. You see what I mean? They're still in there. And clams got legs, as they say in BC. They tend to wind up in places you don't see them, and they quietly and silently kill you. So conduct an audit to get rid of all the common plastics and all the exposed conductors that are capable of lighting a zap flash with which that device might possibly come into contact. Is that straightforward? That's the whole thing in a nutshell. Wet your rugs, buy plastics which keep themselves wet. Cover your doorknobs. Get rid of every nickel-faced bag, every black conductive bag, anything with an exposed metal that can make a spark. Get them out of your system. Use the antistatic ones or the shielding ones with buried layers. The way you can check that rather quickly, we have two bags here. This looks like the aluminum foil is exposed, but it isn't, and you drop a radio in that and it shuts up, right? That's a Faraday cage. Any bag that you can see through permits light to go through it, right? And RF and light are only differing wavelengths in the electromagnetic spectrum. If you can see through it, RF goes through it. The one exception being heavy wire mesh that has enough mass that if you beat it flat, it will become a sheet of foil. Sometimes you have to go so far as to shield against straight magnets. For example, a foil-bearing bag wrapped around a floppy disk and a small pocket magnet wiped off it will eliminate your data. There is a brand new thing called iron foil that's been galvanized. It fits in between these and replaces the aluminum foil. It's made by an outfit called Aegis or handled by an outfit called Aegis, which means shield up in Barrington, Illinois. But that's iron foil. And a magnet over that will not affect the data on a floppy disk. It's also a very much better shield in some ranges for electromagnetic emission. I want you all to know we can't cover the whole problem of ESD and EMI that it produces in a single session. It's like trying to teach the Chinese language in just one set. But I want you all to know that of all the groups I have ever addressed, this is certainly one of them. If you have any questions, I'm some idiot named Dan Anderson, Anderson Effects in Mentone, California. Call me up. I'm one of the better, cheaper acts. Thank you, and God bless you all. Questions, anyone? Yes, the gentleman has a question.
What about the grid bags?
What about the grid bags?
A bag that's got a buried grid in it.
Yeah, the buried grid bags act like the same way. There's a printed carbon grid. As a matter of fact, I designed them. But they were to divert your finger. You know, when you were trying to bring your finger and throw a spark at something through that, you would hit the grid first and go somewhere else, right? It is not by any means as effective a protection or diversion as a solid metallization, and none of those as good as aluminum foil, okay? Aluminum foil, unfortunately, you can't see through, and occasionally the customs likes to look through your device. And the aluminum foil is the ultimate barrier, or the iron foil is even better. But you sort of protect against things in the order of requirement. First you get pink plastics. All of those things that are almost every static shielding bag is lined with pink plastic. In other words, pink poly, so that they don't charge on separation. Then the other layers are on there for additional push, and you can go up depending on what you actually encounter. You know, if you wrap everything in pink polyethylene alone and still lose devices, which nobody ever has, you might move up to the static shielding one, but always one with a buried layer, because why would you take a tabletop where you have buried the metal and put several metal-faced bags on it, man? You've got your doorknob back any way you play it. However, 3M likes to demonstrate the fact that has a conductor on it, man. They put a dime over here and a dime over here and connect it. They can prove that's conductive. I said, I have a better test for you, so you take that one, and I'll take the one with the same amount of metal but buried, right? We both stand in the bathtub and touch 220 with our respective bags. Survivor to have the business. No, don't do that. Come on. Yes, ma'am. The lady with the hair. Blue bins and blue bags. Yes, ma'am. An outfit called Velostat not too long ago produced a pink polycolored blue. It was very good. They simply colored it blue, and its principle was exactly the same. It was a static dissipative material with a migratory antistat in it. Some of the early claims for that, they said, well, it didn't require moisture, it didn't require that, and it turns out it does. You simply, as soon as you pour it, it comes out of the extruder drier than the heart of a sandstorm at high noon in hell, and it will take a static meter. So will pink poly on its initial extrusion. It must get from the atmosphere enough moisture to form that initial layer, you see. On the other hand, from then on it's permanent. However, there are people who would sit there and scrub that for 20 minutes, you know, over the leg and say, jeepers, I can produce some charge on that. Yeah, but that's a little rough. You know, that's not what happens in real life. Does that make any sense? Velostat is very good material. It's, as I say, pink polycolored blue. Anyone else?
Yeah.
Yes, sir.
Your induction example, where you're walking and you're inducing a charge in your body and you test something.
Yes, sir.
You're acquiring charge or getting rid of it.
Well, it doesn't matter whether I acquire it or that acquires it, as long as we be different, you see. That's why the initial contact between any two conductors produces a small spark. How many of you have touched the doorknob and felt the spark? You know what it takes for you to feel that? A 3,500 volt discharge. The human being is incapable of detecting it beneath that. However, it's happening every time you touch a spoon, every time you shake hands, and every time you break two conductors into their initial contact, unless they were very carefully brought to precisely the same level, which is almost impossible to achieve. Whereas if you touch pink or any one of the antistatic materials, the shock comes off sparklessly, and they come to the same polarity without any spark having been exchanged. Does everyone understand that? Does that cover that for you, sir? Does that cover that? Righty, we'll catch you whenever. Anyone else? Anyone else have a question? Yes, sir.
What were the values of the resistors that were being blown?
They were 20th watt, 1 kilo ohm, 0.1% tolerance.
1K.
Mm-hmm. Anyone else? See, I don't know enough about electronics to discuss this accurately. My knowledge of electronics fits accurately under the contact lens. I speak plastics. I think we're plumb out of time, gentlemen, but anybody, you have a question? Yes, sir, I'm sorry.
Yeah, I was kind of confused on the way the pink bag works. You say it's non-conductive, but yet it dissipates static, and the only way you can do that is it conducts internally? Or?
No, it conducts along its surface. It's just a highly resistive conductivity. In other words, it bleeds off static slowly, you know, or bleeds it on slowly.
So it's sort of like, it's like a high resistance.
Precisely. The old trick, for example, when you cross a carpet and you want to reach out and touch a doorknob and it's going to knock the way out of you, you pick up a pink bag, walk over and touch the door with the pink bag, drop the bag and touch the door, and there's no spark because you've drained it, but you've done it sparklessly.
But it's conductive? And
yes, sir, through that water moisture layer on its surface. That's how all of them work.
Okay, but yet if you were to put the continuity meter on it, it would indicate that it would look like an
Yes, sir. You have to test that with surface resistivity according to a thing called ASTM D257-61 originally. And oddly enough, that lies to you because you're passing current through the layer on that, okay? And when you do that, you're boiling the layer off. So you get an artificially high reading for it, okay? Anybody else have a question? Okay, thank you again. God bless you all.
Exciting, exciting presentation. We have a certificate of
Thank
appreciation.
you. Thank you very much.
And we also have a small electronic device that's not in a plastic bag.
Oh,
but,
thank you very much.
Hope it works.
Appreciate it, sir.
All right.
Thank you so much. Thank you all. Yes, sir.